At 10 minutes past 8 on the morning of June 24, 2026, a sudden magnitude 5.6 earthquake disrupted the ordinary geometry of daily life in Mendocino County, Northern California. Within a single 24-hour window, the state's seismic monitoring networks recorded an extraordinary spike in activity, logging approximately 50 distinct earthquakes stretching from the Oregon border all the way down to the edge of Mexico. Yet the most critical element of this geophysical equation was not the localized destruction of cracked roofs in Ukiah, or the tight knots of low-magnitude events crackling across major structural junctions. The defining anomaly of the day was an omission. The San Andreas Fault, the primary tectonic boundary running directly beneath millions of people and carrying a century of accumulated strain, did not move at all. This profound silence on the loudest seismic day of the year presents a fundamental paradox for systems analysis. In the calculus of fault mechanics, absolute quiet is not an indicator of stability or safety. Rather, it is the exact auditory and measurable signature of a locked system that has reached a state of critical deficit. To evaluate this crisis, one must look at the specific parameters established by the United States Geological Survey. The morning rupture occurred near Redwood Valley and Potter Valley at a shallow depth of only 8 kilometers. In seismology, depth is the primary variable governing surface impact. When a strike-slip displacement happens this close to the surface, the kinetic energy has almost no distance to travel, bypassing the crustal attenuation that normally dampens deeper events. The energy arrives at the surface almost entirely intact. This particular event released between 10 to the 13th and 10 to the 14th joules of energy, a metric equivalent to the yield of a small tactical nuclear weapon, applied not as an atmospheric flash but as a mechanical tearing of solid rock. Yet this moderate output belongs to a much larger machine. The epicenter lands on the Mendocino Fault, an inland branch of the vast interconnected plate boundary system driven by the relentless horizontal movement of the Pacific and North American plates. These plates slide past each other at a rate of approximately 1.5 inches per year, a slow grinding that continuously deforms the landscape. The automated systems of California's dense monitoring network mapped this single snap of rock within seconds, illustrating a disturbing systemic boundary. While modern technology can map, measure, and broadcast an earthquake the exact millisecond it initiates, science remains completely incapable of detecting the transition phase immediately preceding the failure. We are highly proficient at archiving the catastrophe, yet entirely blind to its approach. This creates a critical informational void when analyzing the 50 smaller earthquakes that flared across the state on the same day. These flurries occurred at vital structural seams, such as the transition zone where the Calaveras Fault branches away from the San Andreas, and across historical fracture zones in Southern California near Ridgecrest and Bakersfield. When an entire plate boundary lights up simultaneously across hundreds of miles, it alters the regional stress field through Coulomb stress transfer. Every minor rupture redistributes the internal pressure of the crust, loading or unloading adjacent segments. The critical systemic question is whether these 50 minor twitches operated as a safety valve, releasing pressure harmlessly, or if they represent the initial microfractures of a massive interconnected failure. The core mechanical reality is that from the surface both processes look identical. The best instrumentation on Earth cannot distinguish a harmless flurry from the immediate prelude to a macro-scale rupture. This data mismatch leads directly to the mechanism of the silent sections. Unlike the Mendocino Fault, which partially mitigates its stress through steady surface creep, the main trace of the San Andreas is entirely locked. The plates on either side have not stopped moving, meaning the energy is being stored elastically within the bending rock. The silence of the San Andreas on June 24th is therefore full of a dangerous energy deficit, over 120 years of stored motion since the 1906 disaster in the north, and more than 160 years since the 1857 rupture in the south. The system is systematically accumulating a slip deficit measured in tens of feet of impending displacement. What occurs inside a complex mechanical network when every secondary component is visibly vibrating and shifting loads, while the primary structural column remains frozen, absorbing the entire shifting weight of a continental plate without making a sound. To understand how a system hides its ultimate limits, we must examine the specific mechanics of the fault that did rupture. The Mendocino Fault operates under an architectural illusion known as fault creep. At the surface near Ukiah and Willits, the crust appears to release strain through steady, continuous aseismic displacement. Instruments track this surface creep at a rate of 4.5 millimeters per year near Ukiah and 5 millimeters per year near Willits. In places like Hollister, this displacement is visible in offset sidewalks and warped walls, creating a superficial narrative of a self-regulating system. This is a fundamental misinterpretation of the energy budget. Satellite-based geodesy reveals that the deep tectonic drive forces this entire landscape at a rate of 10 to nearly 14 millimeters per year. The resulting mathematical delta is a critical slip deficit. Below a depth of 5 kilometers, the rock transitions from a fluid sliding state to a rigid high-friction grip. Here, the creeping upper layers actively accumulate stress onto immobile, locked patches known as asperities. The peaceable crawling observed at the surface is not a safety valve. It is the mechanism actively loading a deep lithospheric spring. When these deeper asperities reach their structural limits, the resulting failure is not a moderate shock, but a macro-scale rupture. Paleoseismic records extracted from soil trenches near Willits and Ukiah confirm that the Macama is fully capable of generating earthquakes between magnitude 7.0 and 7.6. Each whole number step on the seismic scale represents a 32-fold increase in radiated energy. A magnitude 7.5 event releases hundreds of times the energy of the morning's 5.6 fracture. A rupture of this scale directly threatens the dense infrastructure of the inland valleys and the city of Santa Rosa, home to nearly 200,000 people. The structural consequences would transition instantly from cosmetic wall cracks to systemic failure, the collapse of unreinforced historical masonry, simultaneous ruptures across municipal gas and water distribution networks, and massive landslides isolating critical mountain corridors. This creates a severe logistical lock, trapping rural populations and overwhelming localized medical infrastructure entirely cut off from the broader state grid. On days of heightened seismic activity, superficial interpretations frequently seek explanations outside the boundaries of the immediate geophysical system. Observers point to concurrent minor swarms at Mount Rainier, low-magnitude events at Yellowstone, or variations in solar activity. Systems analysis dismantles these correlations entirely. During this specific sequence, solar data confirmed a quiet sun with no major geomagnetic storm in progress, and the volcanic swarms remained far below baseline thresholds. No physical mechanism links solar radiation or distant magmatic plumbing to a strike-slip displacement in Mendocino County. The energy budget of this crisis is entirely self-contained, written exclusively in the strain accumulation of the localized rock. The ultimate source of this localized strain lies further northwest, at the edge of the continental shelf where the land terminates near Cape Mendocino. This is the Mendocino Triple Junction, a geologically tortured nexus where 3 distinct tectonic plates intersect: the Pacific, the North American, and the Gorda. Here, the clean horizontal mechanics of the San Andreas transform system collide with an entirely different structural dynamic. While the Pacific plate slides northwest, the smaller, younger Gorda plate is actively driven downward, subducting beneath the North American continent. Squeezed from all sides, the Gorda plate crumples internally like a thin sheet of ice compressed in a giant vise, generating violent intraplate fractures. This engine room produces more magnitude 6.0 or greater events than any other region in California, a reality demonstrated by the 1992 Cape Mendocino sequence, where a magnitude 6.9 shock and 2 subsequent magnitude 6.0 ruptures permanently alter the coastline, lifting the seafloor itself above the waterline. This junction serves as the physical hinge connecting California's sideways grinding to the immense downward thrust of the Cascadia subduction zone. It is the upstream headwaters of stress, continuously redrawing the regional strain map and feeding a steady current of mechanical pressure down through the Macama, through the Calaveras, and directly into the primary, silent core of the San Andreas. The structural reality of an interconnected fault network means that the silence of the San Andreas cannot be divorced from the historical data of its past ruptures. To evaluate the true potential of the current energy deficit, systems analysis must look back to 18 seconds past 5:12 a.m. on April 18, 1906. On that morning, the northern segment of the San Andreas Fault underwent a catastrophic failure, ripping open across nearly 300 miles of its length at thousands of miles per hour. This magnitude 7.9 event fundamentally reshaped the landscape, generating horizontal displacements of up to 20 feet. The immediate physical shaking collapsed buildings and buckled municipal streets, but the primary destruction was caused by a cascading failure of modern urban dependencies. The ground motion simultaneously severed municipal water mains and fractured the underground gas distribution lines that fueled the city's heating and lighting. With gas escaping freely and the fire department stripped of its supply, dozens of isolated ignitions rapidly coalesced into a contiguous firestorm that burned for 3 days, ultimately destroying 80% of the urban core and claiming approximately 3,000 lives. This historical footprint reveals that a macro-scale earthquake in a high-density zone is never a singular isolated event. It is a trigger mechanism for a wider infrastructure collapse. When applied to the modern Bay Area, the scale of this vulnerability expands exponentially. While modern engineering and strict building codes ensure that many structures will survive the initial kinetic shockwaves without immediate structural failure, the sheer volume of interconnected assets complicates the recovery matrix. The current urban landscape holds millions more residents and millions more miles of vulnerable pipelines, electric grids, and digital networks than it did a century ago. A repeat of the 1906 rupture would not merely damage localized physical structures, it would instantaneously sever the water, power, and transit lifelines that sustain a highly complex regional economy, creating cascading logistics failures felt across the entire nation. The baseline mechanical issue is that the northern San Andreas has spent the last 120 years since 1906 silently reloading its energy reservoir from zero. Given a constant plate velocity of approximately 1.5 inches per year, the fault has accumulated roughly 15 feet of unreleased horizontal strain. On the southern segment of the fault, which has remained completely locked since the magnitude 7.9 Fort Tejon earthquake of 1857, the unreleased displacement deficit now exceeds 20 feet. Geologists mapping the Carrizo Plain can read the physical scars of 1857 in streambeds sheared and offset by tens of feet during a single morning. Paleoseismic trenching confirms that this southern segment operates on a recurrence interval of 1 to 2 centuries, meaning the system is currently performing at the extreme end of its historical tolerance. This immense accumulation of mechanical force brings the investigation directly to the ultimate variable in urban seismic risk, the Hayward Fault. While the San Andreas carries a higher absolute energy capacity, it runs largely through open ridges and coastal valleys. The Hayward Fault runs directly beneath the urban core of the East Bay, cutting straight through Berkeley, Oakland, Hayward, and Fremont. It is threaded directly through the foundations of apartment complexes, schools, major freeways, and critical hospitals, making it the most urbanized fault line in the United States. While the Makama Fault leaked minor amounts of stress into the northern hills on June 24th, the Hayward Fault maintained a state of absolute immobilization. In the rigid grammar of fault mechanics, this total lack of acoustic or kinetic output indicates a system that is fully locked, heavily loaded, and advancing toward its absolute structural limit beneath the feet of 7 million people. The systemic threat posed by the Hayward Fault is compounded by its historical predictability, which contrasts sharply with the erratic behavior of other segments in the San Andreas network. Paleoseismic data shows that the Hayward Fault has a highly disciplined recurrence schedule, rupturing with a major earthquake roughly every 140 years. The last major event on this specific segment occurred in 1868, when a powerful magnitude 6.8 rupture devastated the East Bay, tearing open the ground and collapsing structures throughout the region. Simple chronologic accounting reveals that the Hayward Fault has passed the exact limit of its historical baseline, operating in a highly critical temporal window. Despite this high probabilities exposure, the fault trace remained entirely silent on June 24, 2026. This complete absence of movement cannot be interpreted as a pause in the tectonic engine. It means that the fault is matching its historical schedule with absolute rigidity, holding fast against the plate motion and storing 158 years of uninterrupted friction and strain right beneath a dense, modern metropolitan corridor. When this structural limit is breached, the primary impact will manifest as a severe physical crisis across the built environment. Because the fault line physically cuts through the urban backbone of the East Bay, the initial horizontal displacement will tear through thousands of structures simultaneously. The foundations of apartment complexes, municipal schools, and critical healthcare facilities will be sheared apart at the moment of rupture. Major transportation networks, including key interstate freeways and rapid transit corridors, will experience instantaneous roadway offsets that render them unusable, blocking emergency response routes and halting the movement of supplies. Simultaneously, the subterranean infrastructure will face catastrophic failure. High-pressure gas transmission pipelines and major water mains will be severed where they cross the fault trace, mimicking the exact infrastructure failure cascade that destroyed San Francisco in 1906. This infrastructure failure introduces the immediate human factor into the crisis matrix. Unlike the rural population density surrounding the Makama Fault, a major rupture on the Hayward Fault directly impacts 7 million people. The failure of localized medical centers means that the injured cannot be treated within the immediate disaster zone, while the destruction of highway corridors prevents the rapid evacuation of casualties to external trauma units. Furthermore, the simultaneous rupture of water mains means that emergency crews will have no municipal water supply to combat the multiple post-earthquake fires that inevitably ignite when underground gas lines breach. This creates a severe logistical paralysis, Millions of residents trapped in a high-density urban corridor with collapsing shelter, zero functional utilities, no running water, and active fire zones moving through the wreckage. This stark projection exposes the ultimate limitation of the characteristic earthquake model, a traditional framework that assumes faults behave like predictable, resetting machines that repeat identical cycles. The reality revealed by modern systems analysis is far messier. Faults do not always break in tidy, isolated segments on a neat schedule, as demonstrated by the famous failure of the Parkfield prediction experiment, where a highly monitored segment arrived decades late and with zero detectable precursors. Instead, the crust operates as a complex dynamic system subject to supercycles, where a fault can store energy across multiple regular intervals and then release it all at once in an unexpectedly massive rupture. On a day when 50 smaller earthquakes rearranged the stress field of California, the silence of the primary locked segments confirms that the regional energy budget is not being safely or gradually drawn down. It is accumulating toward an absolute threshold where the entire interconnected boundary will snap back to its unbent state, executing a violent rebalancing of the continent along a mechanical line that has reached its structural limit. The ultimate realization of this geophysical analysis is that California's dense infrastructure is built entirely upon an active, high-intensity tectonic machine that refuses to conform to human expectations of predictability. The core lesson of the June 24th sequence is that the noise and the silence must be read as a single unified signal. When the Mendocino Fault ruptured north of Ukiah, it cracked roofs and disrupted an ordinary morning, but it also demonstrated the precise boundaries of localized risk. For the residents of Redwood Valley, this sudden ground motion was not an abstract scientific metric, it was a physical convergence of natural hazards, overlapping with the memories of the catastrophic 2017 wildfires that had previously decimated their community. This intersection of environmental pressures highlights the extreme vulnerability of human populations living along a plate boundary, where the Earth possesses multiple avenues for transforming an ordinary workday into a sudden logistical and structural catastrophe. However, looking strictly at the localized impact of a magnitude 5.6 event obscures the true mechanical scale of the crisis. Systems analysis dictates that we move past superficial relief and confront the severe reality of the deep lithospheric energy budget. Within minutes of the morning rupture, the National Tsunami Warning Center confirmed that no tsunami threat existed. This operational detail confirms that the event was entirely a strike-slip inland displacement, a sideways grinding of dry land that lacks the vertical seafloor displacement required to generate ocean-crossing waves. The true hazard of this system is not water, it is the structural lock embedded within the dry land itself. By tracking the horizontal movement of the plates, scientists have mapped out exactly how much strain is being pumped into these locked segments every single year, confirming that the silent faults are actively absorbing a colossal deficit that must eventually be resolved through kinetic release. This realization exposes the profound intelligence gap that remains at the center of modern earthquake science. We have constructed one of the most sensitive automated listening networks on the planet, capable of detecting a rupture the millisecond it initiates, instantly calculating its magnitude, mapping its epicenter, and crowdsourcing citizen intensity reports within minutes. Yet, for all this technological sensitivity, the system is fundamentally reactive. Science remains entirely helpless at predicting the exact moment the rock will reach its ultimate breaking point. A locked fault that is 1 year from an absolute structural collapse looks identical to a locked fault that is 50 years away. Both are completely quiet, offering no precursory acoustic signals, no physical warnings, and no data that human instruments can exploit to mitigate the impending impact. This brings the investigation to its logical, sobering conclusion. The true story of this seismic day is not written in the 50 small earthquakes that shook the state, nor in the cracked walls of Ukiah. The true story is written in the absolute immobility of the San Andreas and Hayward faults. These primary structural columns are not sleeping. They are locked, loading, and systematically withholding a massive century-long energy accumulation. The silence observed across these densely populated corridors on June 24th is the definitive sound of a planetary boundary operating at its extreme mechanical limit. Tectonic forces are indifferent to human history, municipal planning, or the millions of lives established above the fault lines. The strain continues to accumulate, 1.5 inches per year every year without pause. The system will inevitably balance its equation, and the ongoing quiet does not